Neptune is the eighth and farthest known planet from the Sun in the Solar System. In the Solar System, it is the fourth largest planet by diameter, the third most massive planet, and the densest giant planet. Neptune is 17 times the mass of Earth, slightly more massive than its near twin Uranus. Neptune is denser and physically smaller than Uranus because its greater mass causes more gravitational compression of its atmosphere. Neptune orbits the Sun once every 164.8 years at an average distance of 30.10, 4.5 billion km, 2.8 billion mile. It is named after the Roman god of the sea and has the astronomical symbol a stylized version of the god Neptune's trident. Neptune is not visible to the unaided eye and is the only planet in the Solar System found by mathematical prediction rather than by empirical observation. Unexpected changes in the orbit of Uranus led Alexis Bouvard to deduce that its orbit was subject to gravitational perturbation by an unknown planet. The position of Neptune was subsequently calculated from Bouvard's observations, independently, by John Couch Adams and Urbain Le Verrier after his death. Neptune was subsequently observed with a telescope on September 23, 1846 by Johann Galle within a degree of the position predicted by Le Verrier. Its largest moon, Triton, was discovered shortly thereafter, though none of the planet's remaining known 13 moons were located telescopically until the 20th century. The planet's distance from Earth gives it a very small apparent size, making it challenging to study with Earth-based telescopes. Neptune was visited by Voyager 2, when it flew by the planet on August 25, 1989. The advent of the Hubble Space Telescope and large ground-based telescopes with adaptive optics has recently allowed for additional detailed observations from afar. Like Jupiter and Saturn, Neptune's atmosphere is composed primarily of hydrogen and helium, along with traces of hydrocarbons and possibly nitrogen, though it contains a higher proportion of ices such as water, ammonia and methane. However, similar to Uranus, its interior is primarily composed of ices and rock. Uranus and Neptune are normally considered ice giants to emphasize this distinction. Traces of methane in the outermost regions in part account for the planet's blue appearance. In contrast to the hazy, relatively featureless atmosphere of Uranus, Neptune's atmosphere has active and visible weather patterns. For example, at the time of the Voyager 2 flyby in 1989, the planet's southern hemisphere had a great dark spot comparable to the Great Red Spot on Jupiter. These weather patterns are driven by the strongest sustained winds of any planet in the Solar System, with recorded wind speeds as high as 2,100 km per hour, 580 meters per second, 1,300 miles per hour. Because of its great distance from the Sun, Neptune's outer atmosphere is one of the coldest places in the Solar System, with temperatures at its cloud tops approaching 55 K, minus 218 degrees Celsius, minus 361 degrees Fahrenheit. Temperatures at the planet's center are approximately 5,400 K, 5,100 degrees Celsius, 9,300 degrees Fahrenheit. Neptune has a faint and fragmented ring system, labeled arcs, which was discovered in 1984. Then later confirmed by Voyager 2. History. Discovery. Some of the earliest recorded observations ever made through a telescope, Galileo's drawings on December 28, 1612 and January 27, 1613 contain plotted points that match up with what is now known to be the position of Neptune. On both occasions, Galileo seems to have mistaken Neptune for a fixed star when it appeared close, in conjunction, to Jupiter in the night sky. Hence, he is not credited with Neptune's discovery. At his first observation in December 1612, Neptune was almost stationary in the sky because it had just turned retrograde that day. This apparent backward motion is created when Earth's orbit takes it past an outer planet. Because Neptune was only beginning its yearly retrograde cycle, the motion of the planet was far too slight to be detected with Galileo's small telescope. In 2009, a study suggested that Galileo was at least aware that the star he had observed had moved relative to the fixed stars. In 1821, Alexis Bouvard published astronomical tables of the orbit of Neptune's neighbor Uranus. Subsequent observations revealed substantial deviations from the tables, leading Bouver to hypothesize that an unknown body was perturbing the orbit through gravitational interaction. In 1843, John Couch Adams began work on the orbit of Uranus using the data he had. He requested extra data from Sir George Airy, the Astronomer Royal, who supplied it in February 1844. Adams continued to work in 1845 to 46 and produced several different estimates of a new planet. In 1845 to 46, Urbain Le Verrier, independently of Adams, developed his own calculations but aroused no enthusiasm in his compatriots. In June 1846, upon seeing Le Verrier's first published estimate of the planet's longitude and its similarity to Adams's estimate, Airy persuaded Shapley to search for the planet. Shapley vainly scoured the sky throughout August and September. Meanwhile, Le Verrier by letter urged Berlin Observatory astronomer Johann Gottfried Galle to search with the observatory's refractor. Heinrich de Rest, a student at the observatory, suggested to Galle that they could compare a recently drawn chart of the sky in the region of Le Verrier's predicted location with the current sky to seek the displacement characteristic of a planet, as opposed to a fixed star. On the evening of September 23, 1846, the day Galle received the letter, he discovered Neptune just northeast of Phi Aquarii, 1 degree from where Le Verrier had predicted it to be, about 12 degrees from Adams' prediction, and on the border of Aquarius and Capricornus according to the modern Ial constellation boundaries. Shapley later realized that he had observed the planet twice, on 4 and 12 of August, but did not recognize it as a planet because he lacked an up-to-date star map and was distracted by his concurrent work on comet observations. In the wake of the discovery, there was a heated nationalistic rivalry between the French and the British over who deserved credit for the discovery. Eventually, an international consensus emerged that Le Verrier and Adams deserved joint credit. Since 1966, Dennis Rollins has questioned the credibility of Adams's claim to co-discovery, and the issue was re-evaluated by historians with a return in 1998 of the Neptune Papers, historical documents, to the Royal Observatory, Greenwich. After reviewing the documents, they suggest that Adams does not deserve equal credit with Le Verrier for the discovery of Neptune. That credit belongs only to the person who succeeded both in predicting the planet's place and in convincing astronomers to search for it. Naming. Shortly after its discovery, Neptune was referred to simply as the planet exterior to Uranus or as Le Verrier's planet. The first suggestion for a name came from Galle, who proposed the name Janus. In England, Shapley put forward the name Oceanus. Claiming the right to name his discovery, Le Verrier quickly proposed the name Neptune for this new planet, though falsely stating that this had been officially approved by the French Bureau des Longitudes. In October, he sought to name the planet Le Verrier, after himself, and he had loyal support in this from the observatory director, François Arago. This suggestion met with stiff resistance outside France. French almanacs quickly reintroduced the name Herschel for Uranus, after that planet's discoverer Sir William Herschel, and Le Verrier for the new planet. Struve came out in favor of the name Neptune on December 29, 1846, to the St. Petersburg Academy of Sciences. Soon, Neptune became the internationally accepted name. In Roman mythology, Neptune was the god of the sea, identified with the Greek Poseidon. The demand for a mythological name seemed to be in keeping with the nomenclature of the other planets, all of which, except for Earth, were named for deities in Greek and Roman mythology. Most languages today use some variant of the name Neptune for the planet. Indeed, in Chinese, Vietnamese, Japanese, and Korean, the planet's name was translated as Sea King Star. In Mongolian, Neptune is called Dlain Van, reflecting its namesake god's role as the ruler of the sea. In modern Greek, the planet is called Poseidon, by Omicron Sigma Epsilon Iota Delta Nu Alpha Sigma, Poseidonus, the Greek counterpart of Neptune. In Hebrew, Rahab, from a biblical sea monster mentioned in the Book of Psalms, was selected in a vote managed by the Academy of the Hebrew Language in 2009 as the official name for the planet, even though the existing Latin term Neptune, is commonly used. In Maori, the planet is called Tangaroa, named after the Maori god of the sea. In Nahuatl, The planet is called Tlaloc, named after the rain god Tlaloc. In Thai, Neptune is referred both by its westernized name Dao Neptune, and is also named Dao Ketu, star of Ketu, after the descending lunar node Ketu, who plays a role in Hindu astrology. Status. From its discovery in 1846 until the discovery of Pluto in 1930, Neptune was the farthest known planet. When Pluto was discovered, it was considered a planet, and Neptune thus became the second farthest known planet, except for a 20-year period between 1979 and 1999 when Pluto's elliptical orbit brought it closer than Neptune to the Sun. The discovery of the Kuiper Belt in 1992 led many astronomers to debate whether Pluto should be considered a planet or as part of the Kuiper Belt. In 2006, the International Astronomical Union defined the word planet for the first time, reclassifying Pluto as a dwarf planet and making Neptune once again the outermost known planet in the solar system. Physical characteristics. Neptune's mass of 1.0243 times 1026 kilograms is intermediate between Earth and the larger gas giants. It is 17 times that of Earth but just 1/19th that of Jupiter. Its gravity at 1 bar is 11.15 meters/s2, 1.14 times the surface gravity of Earth, and surpassed only by Jupiter. Neptune's equatorial radius of 24,764 kilometers is nearly 4 times that of Earth. Neptune, like Uranus, is an ice giant, a subclass of giant planet, because they are smaller and have higher concentrations of volatiles than Jupiter and Saturn. In the search for extrasolar planets, Neptune has been used as a metonym. Discovered bodies of similar mass are often referred to as Neptunes, just as scientists refer to various extrasolar bodies as Jupiters. Internal structure. Neptune's internal structure resembles that of Uranus. Its atmosphere forms about 5% to 10% of its mass and extends perhaps 10% to 20% of the way towards the core, where it reaches pressures of about 10 gigapascals, or about 100 times that of Earth's atmosphere. Increasing concentrations of methane, ammonia and water are found in the lower regions of the atmosphere. The mantle is equivalent to 10 to 15 Earth masses and is rich in water, ammonia and methane. As is customary in planetary science, this mixture is referred to as icy even though it is a hot, dense fluid. This fluid, which has a high electrical conductivity, is sometimes called a water-ammonia ocean. The mantle may consist of a layer of ionic water in which the water molecules break down into a soup of hydrogen and oxygen ions, and deeper down superionic water in which the oxygen crystallizes but the hydrogen ions float around freely within the oxygen lattice. At a depth of 7,000 kilometers, the conditions may be such that methane decomposes into diamond crystals that rain downwards like hailstones. Scientists also believe that this kind of diamond rain occurs on Jupiter, Saturn, and Uranus. Very high-pressure experiments at the Lawrence Livermore National Laboratory suggest that the top of the mantle may be an ocean of liquid carbon with floating solid diamonds. The core of Neptune is likely composed of iron, nickel and silicates, with an interior model giving a mass about 1.2 times that of Earth. The pressure at the center is 7 bar, 700 gigapascals, about twice as high as that at the center of Earth, and the temperature may be 5,400 K. Atmosphere. At high altitudes, Neptune's atmosphere is 80% hydrogen and 19% helium. A trace amount of methane is also present. Prominent absorption bands of methane exist at wavelengths above 600 nanometers, in the red and infrared portion of the spectrum. As with Uranus, this absorption of red light by the atmospheric methane is part of what gives Neptune its blue hue, although Neptune's vivid azure differs from Uranus's milder cyan. Because Neptune's atmospheric methane content is similar to that of Uranus, some unknown atmospheric constituent is thought to contribute to Neptune's color. Neptune's atmosphere is subdivided into two main regions, the lower troposphere, where temperature decreases with altitude, and the stratosphere, where temperature increases with altitude. The boundary between the two, the tropopause, lies at a pressure of 0.1 bars, 10 kilopascals. The stratosphere then gives way to the thermosphere at a pressure lower than 10-5 to 10-4 bars, 1 to 10 pascals. The thermosphere gradually transitions to the exosphere. Models suggest that Neptune's troposphere is banded by clouds of varying compositions depending on altitude. The upper-level clouds lie at pressures below 1 bar, where the temperature is suitable for methane to condense. For pressures between 1 and 5 bars, 100 and 500 kilopascals, clouds of ammonia and hydrogen sulfide are thought to form. Above a pressure of 5 bars, the clouds may consist of ammonia, ammonium sulfide, hydrogen sulfide and water. Deeper clouds of water ice should be found at pressures of about 50 bars, 5.0 megapascals, where the temperature reaches 273 K, 0 degrees Celsius. Underneath, clouds of ammonia and hydrogen sulfide may be found. High-altitude clouds on Neptune have been observed casting shadows on the opaque cloud deck below. There are also high-altitude cloud bands that wrap around the planet at constant latitude. These circumferential bands have widths of 50 to 150 kilometers and lie about 50 to 110 kilometers above the cloud deck. These altitudes are in the layer where weather occurs, the troposphere. Weather does not occur in the higher stratosphere or thermosphere. Unlike Uranus, Neptune's composition has a higher volume of ocean, whereas Uranus has a smaller mantle. Neptune's spectra suggest that its lower stratosphere is hazy due to condensation of products of ultraviolet photolysis of methane, such as ethane and ethane. The stratosphere is also home to trace amounts of carbon monoxide and hydrogen cyanide. The stratosphere of Neptune is warmer than that of Uranus due to the elevated concentration of hydrocarbons. For reasons that remain obscure, the planet's thermosphere is at an anomalously high temperature of about 750 K. The planet is too far from the Sun for this heat to be generated by ultraviolet radiation. One candidate for a heating mechanism is atmospheric interaction with ions in the planet's magnetic field. Other candidates are gravity waves from the interior that dissipate in the atmosphere. The thermosphere contains traces of carbon dioxide and water, which may have been deposited from external sources such as meteorites and dust. Magnetosphere. Neptune resembles Uranus in its magnetosphere, with a magnetic field strongly tilted relative to its rotational axis at 47 degrees and offset at least 0.55 radii, or about 13,500 kilometers from the planet's physical center. Before Voyager 2's arrival at Neptune, it was hypothesized that Uranus's tilted magnetosphere was the result of its sideways rotation. In comparing the magnetic fields of the two planets, scientists now think the extreme orientation may be characteristic of flows in the planet's interiors. This field may be generated by convective fluid motions in a thin spherical shell of electrically conducting liquids, probably a combination of ammonia, methane and water, resulting in a dynamo action. The dipole component of the magnetic field at the magnetic equator of Neptune is about 14 microtslas, 0.14 g. The dipole magnetic moment of Neptune is about 2.2 times 1017 t middle.m3, 14 mu t middle.r.n. 3, where Rn is the radius of Neptune. Neptune's magnetic field has a complex geometry that includes relatively large contributions from non-dipolar components, including a strong quadrupole moment that may exceed the dipole moment in strength. By contrast, Earth, Jupiter and Saturn have only relatively small quadrupole moments, and their fields are less tilted from the polar axis. The large quadrupole moment of Neptune may be the result of offset from the planet's center and geometrical constraints of the field's dynamo generator. Neptune's bow shock, where the magnetosphere begins to slow the solar wind, occurs at a distance of 34.9 times the radius of the planet. The magnetopause, where the pressure of the magnetosphere counterbalances the solar wind, lies at a distance of 23 to 26.5 times the radius of Neptune. The tail of the magnetosphere extends out to at least 72 times the radius of Neptune, and likely much farther. Climate. Neptune's weather is characterized by extremely dynamic storm systems, with winds reaching speeds of almost 600 meters per second, 2,200 kilometers per hour, 1,300 miles per hour, nearly reaching supersonic flow. More typically, by tracking the motion of persistent clouds, wind speeds have been shown to vary from 20 meters per second in the easterly direction to 325 meters per second westward. At the cloud tops, the prevailing winds range in speed from 400 meters per second along the equator to 250 meters per second at the poles. Most of the winds on Neptune move in a direction opposite the planet's rotation. The general pattern of winds showed prograde rotation at high latitudes versus retrograde rotation at lower latitudes. The difference in flow direction is thought to be a skin effect and not due to any deeper atmospheric processes. At 70 degrees S latitude, a high-speed jet travels at a speed of 300 meters per second. Neptune differs from Uranus in its typical level of meteorological activity. Voyager 2 observed weather phenomena on Neptune during its 1989 flyby, but no comparable phenomena on Uranus during its 1986 flyby. The abundance of methane, ethane and acetylene at Neptune's equator is 10 to 100 times greater than at the poles. This is interpreted as evidence for upwelling at the equator and subsidence near the poles because photochemistry cannot account for the distribution without meridional circulation. In 2007, it was discovered that the upper troposphere of Neptune's south pole was about 10 K warmer than the rest of its atmosphere, which averages approximately 73 K, minus 200 degrees Celsius. The temperature differential is enough to let methane, which elsewhere is frozen in the troposphere, escape into the stratosphere near the pole. The relative hot spot is due to Neptune's axial tilt, which has exposed the South Pole to the Sun for the last quarter of Neptune's year, or roughly 40 Earth years. As Neptune slowly moves towards the opposite side of the Sun, the South Pole will be darkened and the North Pole illuminated, causing the methane release to shift to the North Pole. Because of seasonal changes, the cloud bands in the southern hemisphere of Neptune have been observed to increase in size and albedo. This trend was first seen in 1980 and is expected to last until about 2020. The long orbital period of Neptune results in seasons lasting 40 years. Storms. In 1989, the Great Dark Spot, an anticyclonic storm system spanning 13,000 times 6,600 kilometers, was discovered by NASA's Voyager 2 spacecraft. The storm resembled the Great Red Spot of Jupiter. Some 5 years later, on November 2, 1994, the Hubble Space Telescope did not see the Great Dark Spot on the planet. Instead, a new storm similar to the Great Dark Spot was found in Neptune's northern hemisphere. The Scooter is another storm, a white cloud group farther south than the Great Dark Spot. This nickname first arose during the months leading up to the Voyager 2 encounter in 1989, when they were observed moving at speeds faster than the Great Dark Spot, and images acquired later would subsequently reveal the presence of clouds moving even faster than those that had initially been detected by Voyager 2. The small dark spot is a southern cyclonic storm, the second most intense storm observed during the 1989 encounter. It was initially completely dark, but as Voyager 2 approached the planet, a bright core developed and can be seen in most of the highest resolution images. Neptune's dark spots are thought to occur in the troposphere at lower altitudes than the brighter cloud features, so they appear as holes in the upper cloud decks. As they are stable features that can persist for several months, they are thought to be vortex structures. Often associated with dark spots are brighter, persistent methane clouds that form around the tropopause layer. The persistence of companion clouds shows that some former dark spots may continue to exist as cyclones even though they are no longer visible as a dark feature. Dark spots may dissipate when they migrate too close to the equator or possibly through some other unknown mechanism. Hot Neptune. Neptune in astrology. Neptunium. Neptune, the mystic, one of the 7 movements in Gustav Holst's Planet Suite. Timeline of the far future. Notes. References. Bibliography. Burgess, Eric, 1991. Far Encounter, The Neptune System. Columbia University Press. ISBN 978-0231-074-124. Moore, Patrick, 2000. The Data Book of Astronomy. CRC Press. ISBN 978-07503-06201. Further reading.